All right, let's talk about something absolutely fundamental in geotechnical engineering. We're going to dive into the cornerstone formula that helps us ensure a structure is safe and stable, the general bearing capacity equation. I mean, think about it. You've got this massive structure you're about to build. How can you be absolutely sure the ground underneath it won't just give way? That's the single most important question a foundation engineer has to answer. Get it right, you're golden. Get it wrong, well, the consequences can be catastrophic. Everything we do really boils down to this one critical value, the ultimate bearing capacity, which we call Q sub U. You can think of it as the soil's absolute breaking point. Our entire job is to calculate that limit and then apply a nice big factor of safety so that our building's load isn't even close to it. Okay, so let's get into the main event, the tool we use to figure all this out. Now, I know, when you first see the general bearing capacity equation, it can look like a monster. But trust me, it's actually just three logical pieces stitched together, and each piece tells us something different about where the soil gets its strength. Here it is, broken into its three core parts. The first term is all about cohesion, how well the soil particles stick to each other. The second term, the surcharge term, accounts for the strength we get from the weight of all the soil around the foundation. And that third term, that's about the resistance from the soil directly under the foundation. You add them all up and bam, you get the total picture of the soil's strength. So what's inside these terms? We've got our basic soil properties, right? Things like cohesion, C prime, the effective stress at the bottom of the foundation, Q, and the soil's unit weight, gamma. But the real magic, the part that makes this equation so powerful, comes from all those N and F factors. They're the modifiers that let us tune the equation to our specific project. You see, the original raw formula was developed for a perfect, idealized situation, a super long, continuous footing. But let's be real, we build square foundations, round ones, and we put them at all sorts of different depths. That's exactly where these correction factors come in. They're what bridge the gap from theory to reality. And these F factors aren't just numbers pulled out of thin air. They're the secret sauce, developed from tons of testing. They help us answer really practical questions, like how is a square footing different from a long strip footing? How much stronger does it get if we bury it a few feet deeper? These factors are what make the equation so incredibly versatile for real-world design. Now, before we even get to the F factors, let's look at the N factors. These are tied directly to the soil's internal friction angle. And check this out. Look at how these numbers just explode as the friction angle goes up. Going from 30 to 34 degrees almost doubles N gamma. It's a perfect illustration of just how incredibly important frictional strength is for a soil's capacity. Now for the shape factors. Imagine a really long wall footing. The soil can really only fail by pushing out to two sides. But a square footing, it has backup on all four sides, which makes it way more efficient at mobilizing the soil's strength. These shape factors, like FQs and F gammas, are how we quantify that extra 3D support. Then we have the depth factors. It's pretty intuitive, right? The deeper you put a foundation, the more soil you have pressing in from the sides, basically holding everything together and confining it. That extra pressure makes it harder for the soil underneath to shear and fail. The depth factor, FQD, is simply the mathematical way we account for that bonus strength you get from going deep. Okay, enough theory. Let's get our hands dirty with a practical design problem and see how this all works in the real world. Our mission is to figure out just how big a square foundation needs to be to support a specific load. So here's our setup. We have a 150,000-pound load, and we need a factor of safety of 3. The soil is a sand, so its cohesion is 0, but it has a good friction angle of 34 degrees. Now, pay close attention here. We have two different unit weights. Why? Because the water table is at 2 feet deep, but our foundation bottom is at 4 feet. That is a critical detail that's going to have a huge impact on our calculations. We're not just going to jump in randomly. We've got a game plan, a clear 5-step process that's going to keep us on track and make sure we don't miss anything. We'll simplify the formula, calculate all our inputs, build the final equation, and then solve for the one thing we need, the width, B. First things first, let's clean this equation up. We know our soil is sand, so there's no cohesion. That means the entire first term, gone. It's 0. We also have a simple vertical load, so the inclination factors are all just 1. So we're left with a much simpler equation, just the surcharge term and the soil weight term. And notice that little prime on the gamma? That's our reminder that we have to account for that water table. All right, step 2, calculating Q, the effective stress. And this is where that water table we mentioned really comes into play. You see, the water in the soil's pores doesn't help with strength at all. In fact, its buoyancy actually pushes up, reducing the stress on the soil particles. So for the first 2 feet of dry soil, we use the full unit weight, 105. But for the next 2 feet that are submerged, we have to use the effective unit weight, which is the saturated weight of 118 minus the weight of water, 62.4. Add those two pieces together and we get an effective stress of 321.2 pounds per square foot. Getting this right is absolutely critical. Okay, now for some easier parts. We just look up our friction angle of 34 degrees in the standard bearing capacity tables. That gives us an NQ of 29.44 and an N gamma of 41.06. Simple as that. Let's get the correction factors. For a square footing with a 34-degree friction angle, FQS is 1.67 and F gamma S is 0.6. F gamma D is just 1. But wait a minute, look at the depth factor, FQD. The formula for it has B in it, the foundation width we're trying to find. So we need B to find FQD, but we need FQD to find B. This is a classic engineering puzzle, and it means we can't just solve for B directly. We have to use a good old-fashioned method, trial and error. So here's where it all comes together. On one side of the equation, you have the stress from our building pushing down. That's the 150,000-pound load spread over the area, B squared. And on the other side, you have the strength the soil can safely provide. That's the ultimate capacity, Q sub U, divided by our factor of safety of 3. These two sides have to balance out. Now for the trial and error. Let's just guess a width. How about 4 feet? Okay, the applied stress would be 9,375 pounds per square foot. If we plug B equals 4 into our capacity formula, we find the allowable capacity is only 7,559. So the applied stress is bigger than the allowable capacity. That's a fail, no good. Okay, let's try a bigger size. How about 4.5 feet? Now the applied stress drops to 7,407. The allowable capacity is 7,519. There we go. The applied stress is now less than what the soil can handle. We're safe, it works. And just like that, we've got our answer. To safely support this load,